In this video, we are going to look at some calorimetry problems. First, calorimetry can be used to find the specific heat of a substance. And these are the guiding equations. Actually, both these are representing the same thing. So it's just one guiding equation to find the specific heat of a substance. So let's see the procedure. Let's say you have a metal whose specific heat you're trying to determine. Recall that Q is equal to mc delta T. That means specific heat, if you isolate specific heat in this equation, it's going to be Q over m delta T. That means to find the specific heat, we need to know the mass of the substance, and we need to know how much energy is getting into the substance or out of the substance, and the associated temperature change. If we know those, then we can solve for the specific heat of the metal. However, we know only the mass of the metal. Let's say this metal weighs 25 grams. We can weigh the metal and know the mass of the metal, but we have two unknowns here. Okay, we could supply heat, we could record the temperature change, but we would not know how much heat went into the metal. So just heating this metal up is not going to help you figure out the specific heat. So we are going to be clever about how to find um, uh, the Q, meaning the amount of heat released or absorbed during a temperature change. Basically, what we are going to do is we are going to make the metal give off heat to a substance whose specific heat is known. So we are going to choose a substance such as water whose specific heat is known. So here's what we do. We heat up the metal first. We're going to record the temperature of the hot metal. So let's say we heated it up to 80 degrees Celsius. Okay, now we are going to take water of a known mass. So let's say 30 grams of water. You weigh it out, put it in this styrofoam cup, and then record its temperature. The specific heat of water is a known value. Now we are going to put this hot metal at 80 degrees Celsius into this styrofoam cup. Now what happens is heat exchange between water and the metal. The metal is going to lose heat to the water surrounding it. So metal will lose heat and the temperature of the metal is going to drop, whereas the temperature of the water is going to increase. So let's say the temperature of the water increased to 30 degrees Celsius. So that's the final temperature of water after you wait for some time. Okay, so we call that the equilibrium temperature of water because you want to record it after the temperature has stabilized. Okay, now what is the final temperature of the metal? Think about it. The metal and the water are in contact and they should have reached the same temperature because they're in contact with each other. There should be a thermal equilibrium, meaning they both should be at the same final temperature. So the final temperature of water is also the final temperature of the metal. Okay, so now since we know the mass, specific heat, and the temperature change for the water, we could calculate the Q for the water, meaning the amount of heat absorbed by the water during this temperature change. Okay, so we could plug that out and the units you can see cancel out, grams cancel out, Celsius cancel out, and we're going to end up with joules of heat absorbed by the water. Notice that it's going to be positive because your delta T is positive. The final is greater than initial. So Q is positive, which is suggesting that water has absorbed heat, which is true. Now, where did that heat come from? Well, since this is an insulated system, it's the metal that gave off the heat. That heat did not come from the surroundings. It came from the metal. So we can say the heat absorbed by the metal is equal to the heat absorbed by the water is equal to the heat released by the metal. So we can just say Q water, Q metal is the same as Q water, but with the opposite sign, because if water is absorbing heat, metal is releasing heat. So Q metal will be negative of Q water. That's the equation that I put there. It's important to change the sign because you always record Q along with the sign. Since metal is releasing heat, it's the same value but with opposite sign. So now we know how much heat the metal lost during this temperature change. So when it's going from 80 degrees Celsius, which was hot, to 30 degrees Celsius, which is the final temperature, it would have lost this much amount of heat. So we know the heat, we know the temperature change associated with it, and we know the mass of the metal. So we are going to plug those in into this equation and calculate the specific heat of the metal. So you can plug those values in and you're going to get 0.98 joules per gram degree Celsius. Specific heat can never be negative. If you get negative values for specific heat, probably you didn't convert the sign somewhere. This is negative here, and your delta T is also negative because the final is less than the initial. So the negatives cancel out, and you get a positive value for the specific heat of the metal. Now, you don't have to always choose water. You can choose any substance, but you should know its specific heat in order to find how much heat has been absorbed by that substance. All right, so this is one use of calorimetry to find the specific heat of a substance. You can also use this equation because Q metal is nothing but mass, specific heat, and temperature change for the metal, and Q water is mass, specific heat, and temperature change for the water. So you can plug those in, but notice that you should have opposite signs. So this should be negative here. So you could plug in the values for any of these and calculate an unknown value. So there could be a question where mass of the metal is unknown. There could be a question where the final temperature is unknown or the initial temperature of one of these substances is unknown. So using this equation, you can calculate any one unknown out of these variables. Moving on to another use of calorimetry. Calorimetry can also be used to find the delta H or the enthalpy change of a reaction. Recall that delta H is Q at constant pressure. So if you were able to measure the heat released or absorbed in a reaction at constant pressure, basically what you're measuring is delta H of the reaction. So our styrofoam cup is a constant pressure calorimetry because it is any gases that are released can reach the atmospheric pressure. You're not sealing off this container. So this is a constant pressure calorimetry. Now these are the guiding equations, and we'll look at a problem and see how to use those guiding equations. All right, here's the first question. 4 grams of solid KCl is dissolved in 50 milliliters of water inside a constant pressure calorimeter. As the reaction solution is mixed, the temperature of the solution drops from 24 to 20.02 degrees Celsius. Calculate the delta H of the dissolution process in kilojoules per mole. All right, so if you notice what we have here is a temperature drop, and this is a temperature drop for the solution. So you are taking a solid, this is a salt, potassium chloride salt, you're dissolving it in water. So you have a solution there with water and dissolved KCl. And for that solution, if you stick a temperature probe inside it, you're recording a temperature change. So before KCl is dissolved, it's at 24, and after KCl is dissolved, the temperature got to 20.02 degrees Celsius. What else do we know about this solution? We know the temperature change for the solution. We can also get the mass of the solution. It's basically the solid plus the water. Okay, the contents are basically solid plus the water. And we also can estimate the specific heat of the solution. So let's look at this step by step. We're also going to call this solution as matrix. Matrix basically means all the solution that is there in this calorimeter. And it's for this problem, it's basically the solid KCl dissolved in water. So first, let's get the mass of this matrix. It's going to be mass of the KCl plus mass of water. You know the density of water, that's 1 gram per mil. So 50 milliliters should be 50 grams. So you can cancel the units, milliliters, and go to grams. So 50 milliliters of water is 50 grams. And then you dissolved 4 grams. So add those two masses up and you get the mass of the matrix. Remember, matrix is nothing but the entire solution, okay, after you mix them together. Now, what will be the specific heat of the matrix? Well, most of it is water, so we can assume that it's the same as water. We are making an assumption here that the C matrix, the specific heat of the matrix, is same as the specific heat of water. Next, we need the delta T, the temperature change for the matrix. So that's the initial and that's the final. So your delta T will be final minus initial, which is negative 4.02 degrees Celsius. We have a drop in temperature here. So now using the mass of the matrix, specific heat of the matrix, and delta T of the matrix, you can calculate the Q of the matrix. That means the heat absorbed or released by the matrix. And you can plug the values in, the mass, specific heat, and delta T. And turns out that this temperature change corresponds to 840.9 joules of heat being released by the matrix. Okay, the sign should make sense here because a temperature drop would mean the heat is released, taken away from the matrix. Okay, that's why the matrix is cooling down because it's losing heat. And you can see that clearly here in the sign. Q matrix is negative 840.9 joules. Now, how is Q matrix related to the reaction? Remember, if the matrix is cooling down, that means it is releasing energy. The energy is going into the reaction. Okay, you can say the reaction is absorbing heat from the matrix. That's why the matrix is cooling down. So since the heat transfer is occurring in a calorimeter, which is shielded from the surroundings, heat lost by the matrix is equal to heat that went into the reaction. So we can say Q reaction is opposite of Q matrix. Okay, so we are going to change the sign here. So Q reaction is opposite of Q matrix. Recall that Q at constant pressure is nothing but delta H. So we can say this is also your delta H for the reaction. Okay, so this value is delta H for the reaction. And delta H is positive, means this is an endothermic reaction. Yes, the dissolution process, dissolving KCl, is taking energy from the surrounding water. That's why the surrounding water or the matrix is cooling down. So the dissolution process we have here is endothermic. We are not done yet because we are asked to calculate the delta H of this dissolution process in kilojoules per mole, meaning per mole of the reaction. The reaction is KCl dissolving in water, which is KCl going to K plus, potassium ion, and chloride ion. So per mole of reaction means nothing but per mole of KCl. So we want to know how much is the delta H if we dissolve 1 mole of KCl. So this delta H is for dissolving 4 grams of KCl. 4 grams means that many moles. Dividing by the molecular weight of KCl will tell you how many moles that is. So this number is when 0.05366 moles of KCl is dissolved. Now, how to calculate per mole? Think about the units. You're looking for energy per mole, so you have to divide them. Okay, so per mole, delta H Q reaction per mole is going to be 840.9 divided by that. That's going to tell you how much it is per mole. You can round that off to two significant digits because we have two sig figs here. And that's going to be 16,000 joules per mole of KCl dissolved, which is 16 kilojoules. So basically dividing by 1,000 will turn that to kilojoules. So that's positive 16 kilojoules per mole of KCl dissolved. Now imagine what's going on here. Dissolving a salt has basically cooled down your reaction, okay? So you know about cold packs. When you have injuries, you apply cold pack. A cold pack basically contains a salt such as potassium chloride in one compartment and water in the other compartment. And when you squeeze it, the seal breaks and the KCl and the water mix. And the dissolution of KCl is an endothermic process. It's going to take heat. So the reaction is going to take heat from the solution. That means from the surrounding water, and the surrounding water is going to cool down. And that's how you have an ice pack, meaning you have a you have a cold pack. All right, moving on to another question, but this time it's not a dissolution. Let's see a reaction between an acid and a base. So here's the question. A student adds 25 milliliters of 0.1 molar strong acid to 25 milliliters of 0.12 molar strong base inside a coffee cup calorimeter and immediately places the lid on the top. The solution's temperature rises from 20.5 to 25.0 degrees Celsius. Calculate the delta H in kilojoules per mole of reaction. And we are told that the acid and base react in 1-to-1 stoichiometric ratio. Again, look at the problem, and since this is a calorimetry problem, my eyes are shifting to this. It's a temperature change, okay? And whose temperature change is it? It's the temperature change for the entire solution that is in the calorimeter. So I know the temperature change of the solution, so I need to get the mass of the solution. So remember, we are going to call that entire solution as matrix. So the mass of the matrix is basically the 25 milliliter is, you can assume that if the density of the solution is same as the density of water, so 25 mils will be 25 grams because we're assuming that the solution's density is 1 gram per mil. So 25 milliliters here is also 25 grams. So the total mass of the matrix, that means the contents of the calorimeter after you mix the solutions, is going to be 50 grams. So it is the 50 gram solution that is undergoing this temperature change. Okay, remember this is a temperature change for the solution. The entire matrix, whose weight is 50 grams, is undergoing this temperature change. So specific heat of the matrix, again, we are going to assume it's the same as water. And the delta T of the matrix is final minus initial, 25 minus 20, which is 5 degrees Celsius. Now we are going to multiply them all together to get the Q matrix. And that's, I got 1046 joules. Okay, this is the heat absorbed by the matrix. The matrix is absorbing heat, and that's why its temperature is increasing. Okay, so we got a positive value here, but that's Q matrix. It's not Q reaction. So to get the Q reaction or delta H of the reaction, we change the sign. So it's going to be negative 1046, meaning the reaction is exothermic. The reaction is releasing heat to the matrix. And that's why the matrix was getting heated up. All right, we are not done yet because we are asked to calculate the delta H per mole of reaction. So we need to look at what components are reacting. So if you look at the reaction, it's a 1-to-1 ratio. So I'm going to write it as 1 mole of acid plus 1 mole of base going to products. So we have some information about the acid, the volume, and the molarity are given. So you can do volume in liters times the molarity, and that's going to give you moles. So it's basically 0.025 liters times 0.1 moles per liter, and that's going to give you moles of acid that you reacted. You can do the same thing for the base, and turns out you reacted 0.03 moles of the base. Since the reactant 1-to-1 ratio and the amounts that you mixed are not in the 1-to-1 ratio, one of them is going to be limiting and the other one is in excess. So we can divide the moles by the stoichiometric ratios, so divided by 1 and 1. And you can see that this is in least stoichiometric ratio. That means the acid is your limiting reagent. So the true moles of acid that are reacting is 0.025. And moles of base that are reacting is also 0.025 because acid and base react in 1-to-1 ratio. So we can pick either compound and say this negative 1046 joules is the heat released when 0.025 moles of, I should have said 0.0025. For 0.0025 moles of acid reacting. So now when you divide, you get the amount of energy per mole of acid reacting. So delta H, you can do that. And that's going to give you per mole of acid. We are looking for per mole of reaction. So since there is 1 mole of acid means 1 mole of reaction, since it's a 1-to-1 ratio, so 1 mole of reaction has 1 mole of acid, you can also say this value is going to give you the amount of energy per mole of reaction. Okay, so that's the number I got rounded off to 2 significant digits, which when you convert to kilojoules, since there are 1,000 joules in a kilojoule, the joules cancel out and you get the amount of energy released by the reaction. So it's released because it's negative. So this is the amount of energy released by the reaction you can say released per mole of reaction, or in other words, released per mole of acid that reacts.